So what happens in heat exchangers? We have transfer of heat from the cold stream to the or transfer from the hot stream to the cold stream, and these heat transfers happen through a solid surface that is separating these two streams. If we look at the double pipe heat exchanger, for example, what we have is, let's say, external pipe, and then internally we have another one. Just gonna bring you. So let's say we have this cold stream in the hot stream in the inner side flow pipe, and then cold stream in the outer side, and the heat transfer between the two is happening through this tube wall or the solid wall that we have. And assuming this is di and this is do, what we have here is we have a convection in the outer side of the pipe with the cold stream, convection in the inner side with the hot stream, and then we have conduction through this wall. So if I look at the cross section of this system, so this is the bigger tube or the shell that we have, and internally we have this internal pipe that we are saying there is a cold hot flow in, and there is a cold flow just flowing inside that the system. Now if I look at the small part of that, if I take this wall and just exaggerate here, so this is what we are gonna see. So this is the wall, and at the hot stream, let's say we have a temperature of TH, and heat is just getting transferred by convection, and then we have conductions happening inside the system. This is the conduction, and then we have another stream where it goes to the T of cold, so TH, T of cold. So this is the wall that we are looking at, and the internal surface area of that pipe, let's say this is AI, and with the heat transfer coefficient of HI, the outer side is AO with that heat transfer coefficient of HO. Now, if I just look at the resistance to the heat flow, starting from TH, we have one resistance because of the convection in the hot side. Then we have a RT of conduction for the wall. And then we have another resistance till we are reaching T of T cold, which is convection for the cold side, for the cold fluid. The cold and hot could be in different arrangement. Now, and that's the Q that is flowing through the system. So I can use the overall heat transfer coefficients that we have seen before between any 2 points, temperature difference TH minus T cold divided by 1 over HIAI plus log of DO over DI 2 pi KL plus 1 over HO AO. Consider that I'm assuming the length of each exchanger is L here. So this is the value for QAI for this one. If it's circular, it's going to be pi DIL. AO is going to be pi DOL. Okay. Now definition of, remember, definition of overall heat transfer, or U, that we had. Q was U A delta T overall that we have. Now, if we the A could be evaluated at any side of the heat exchanger or this pipe because the inner surface and outer surface is different. So by comparing these two, UA is gonna be 1 over this property. So I can write down 1 over UA, which can be evaluated at the inner side, UIAI, or at the outer side, UOAO. It's gonna be 1 over HIAI plus natural log of dO over di over 2 pi kl plus 1 over HOAO. Now, when the tube thickness is very small, so this is the overall heat transfer coefficients for the system that we have. In order to evaluate this overall heat transfer coefficient, we need to have the value of HI, HO, which are the convective heat transfer. And we have seen that for the force flow, and we will see if, for the natural convection and condensation boiling too. And another thing here is having the thermal contact, the thermal conductivity resistance because of the thermal conductivity. Now, when the tube thickness is small and the thermal conductivity of material is high, so if tube thickness is small and K is high, generally we choose the material that provides a high conductivity. Then what we can say here is RTF conduction because of the wall is almost zero. If that's zero, and the other thing that we can say is AI, since the thickness is small, is equal almost to AO. So 1 over U is going to be approximately 1 over HI plus 1 over HO. This is the case that the tube thickness is a little bit small or is small and the conductivity is very high. Another part that can happen in a heat exchanger and we need to take into account is fouling factor. Remember that with the use of heat exchanger over a period of time, the tube surfaces become coated with solid deposition. So over time, the tube surfaces become coated. These solid depositions could be whatever that is carrying by the flows that the cold or hot stream, and this coating add additional resistance to the heat transfer by conduction and becomes coated. So this adds additional heat transfer resistance by conduction, and this the increased resistance due to the tube fouling is called fouling factor. So let's say if I just plot the part of the tube that we are looking at, because of these positions, it could be on the inner, outer, it could be different materials, different thickness. So these are the solid deposition, and we need to take into account. So these are adding two resistance because of conduction. So 1 over UA is going to be 1 over HI AI plus all double prime F for the internal surface AI. So this is the resistance because of the falling on the internal surfaces plus natural log of dO over di 2 pi k L, and you're going to have another falling resistance to the outside AO plus 1 over HOAO. So commonly when we design heat exchanger, we design by including or anticipating this fouling that's going to happen. So we have a slightly over design at the beginning But over the time, since this fouling and depositions happens, then we are getting to the actual performance that we want. But over design is better than designing for the non-deposited or uncoated surfaces, and later on we lose the efficiency for the heat exchanger. In case that there are significant fouling, there should be mechanical or chemical cleaning of the tube could be required. So we might need to shut off the heat exchanger and do the cleaning procedure.